Let's keep going in our journey of discovering how the derivatives of f affect f. And here we go into the second derivative. So this lesson is all about concavity. We'll talk about that shortly and what that looks like. And points of inflection. We have studied functions that increase and decrease, I say. So it's time to study now how the first derivative of a function as it increases and decreases and how it changes affects the original function. So we're going to look at f prime and how its rate of change affects f. So the slopes of f prime. So we're going to begin with concavity. So it basically says, given a function f that is differentiable, smooth, continuous, on all real numbers and is concave up. So here we are concave up from a to b. So we'll take a look at that. Here's the graph of f of x. Concave up quite literally looks like you're facing upwards, right? It loosely translates to with cave up. And then concave down would be like from B to C, where we are facing down. Now, we're going to describe the behavior of f prime on these intervals. If you look at the behavior of it, just draw in some tangent lines. Though the tangent lines go from negative to positive here, it's important to note that the tangent lines are getting less negative and then more positive. And then from B to C, the tangent lines are going from positive to negative. But if we look real closely, we're basically saying the tangent lines get less positive and more negative. So in this case, the tangent line slopes are increasing, right? They're getting less negative and more positive, that'd be increasing. And from B to C, our tangent line slopes are going from positive to negative, which means that our tangent lines are decreasing in slope. All right, so that's very key. Those would be the formal ways of looking at concavity. So concave up, concave down. All right, on to the next little part here. It says, what function describes the increase and or decrease, the rate of change of the first derivative? That would be f double prime, right? The derivative of f prime would be f double prime, and that would describe the rate of change of f prime. Or the slopes of f prime would be f double prime. All right, always keep it one level down. F prime, f double prime. Going from f to f double prime, that's, we'll get there. We'll get there very shortly, but for right now, the derivative of f prime is f double prime. F prime is increasing when? Well, again, that's when the slopes are increasing, Well, f prime would be increasing when its derivative is positive. So its derivative is the second derivative. Just like f is increasing when f prime is positive, f prime is increasing when f double prime is positive. And since we know that f prime, by increasing, causes concave up, that also means that f is concave up when f double prime is greater than 0. Very cool. And f prime is decreasing when its derivative is negative. So that'd be when f double prime is less than 0. And so f is concave down, you guessed it, when f double prime is less than 0. So those are the main concepts there. And what we're now going to do is go into two examples using these concepts to figure out when a curve is concave up or concave down. It's very cool. Very, very cool. What you shouldn't do early on, by the way, is think about f prime, and f double prime all at once. So f is concave up when f double prime is positive. F is concave down, like that, when f double prime is negative. You could say the tangent lines are decreasing in slope when f double prime is negative, and they're increasing in slope when f double prime is positive. Go from one level to another, but not all three at once. Okay, so determine the intervals on which the following function is concave up and concave down. So in other words, we need to figure out when f double prime is greater than 0 and f double prime is less than 0. And this will seem very similar to figuring out when f was increasing and decreasing, but we're just going to do it with the second derivative. So I want you to link it to what we did in lesson 3.3. First things first, I have to take two derivatives. I'm going to reset this so I don't have to use the quotient rule. That's x minus 1 to the negative 1. So I'll have to take the first derivative, but I'm interested in the second. So f prime of x, chain rule, derivative of the outside, is minus 1 times x minus 1 to the minus 2. And that simplifies out to be, well, doesn't really matter. You know why? Because we're going to take the derivative of that. So now we're going to take the second derivative. So keep it in negative exponent form because we need the second derivative. Negative 2 times negative 1 is 2 times x minus 1 to the negative 3. At this point, I'm going to rewrite this function as 2 over x minus 1 cubed because we want to figure out where is this positive and where is it negative. Just like with the first derivative, we're going to do the same here. We want to know where the second derivative is 0 or does not exist. It's never going to be equal to 0, but it won't exist at x equals 1, right? So that's because x minus 1, the denominator, will be equal to 0 when x minus 1 is 0. So x equals 1 is a place we want to look for the signs of the second derivative to change. Interesting. So we're really just basically doing the first derivative testing on an interval, but of its derivative. We're doing the same thing. So think of it as like f prime, and now we're going to take its derivative, f double prime, and look and see how the basically tangent lines of f are changing. So x equals 1 is the only place I'm going to look. Now, left of that, 0. 0 minus 1 cubed is negative. 2 over that is still negative. And so what this means is f prime is going to be decreasing. All right, so what does that mean on f? Well, if f prime is decreasing, the slopes are getting less positive or more negative. And so that means on f, we're going to be concave down. Right? Okay, and then here, greater than 1, I don't know, 32. Minus 1 cubed is positive. 2 divided by that, still positive. So f prime is increasing. F prime is increasing. And f is therefore concave up. Your tangent line slopes are either starting out and, well, basically getting less negative or getting more positive. Either way, we're concave up. Now we're cooking. And that's it. So what are your intervals? Well, we're going to be concave up from 1 to infinity. Right? So concave up from 1 to infinity and concave down from negative infinity to 1. Simple as that. Not so bad at all. I'm going to do one more example with you, and I'm not going to do anything with f prime and relating it. I'm just going to go straight up with f double prime. Okay, let's do it. So it says determine the intervals on which the following function is concave up and concave down. Justify your answers. Again, we need two derivatives here because we're really looking to see when g double prime is greater than 0 and where g double prime is less than 0. Let's go for it. So g prime of x is equal to 3x squared minus 12x. We're going to pass right through this because we're looking for g double prime. G double prime of x is equal to 6x minus 12. Again, we're going to set that equal to 0. We're looking basically for the critical numbers of g prime, if you will. And that's going to be when x is equal to 2, right? We add 12 and divide by 6. So x equal to 2 is the only place I need to check on a number line. And remember, I'm checking the g double prime number line. How about that? And so that's at x equals 2. And if we pick a value less than 2, like 0, 0 times 6 minus 12 is, okay, that's going to be negative. So we're concave down. All right, so you could draw a picture like that or just say concave down there. And greater than 2, 45. 45 times 6 minus 12, it's positive. So we're going to be concave up. And that's on g. That's it. That's all. So the interval where we're concave down is going to be from negative infinity to 2, or you could just say x is less than 2. And we're concave up for x is greater than 2. That's all it is. When you take a rough, like a super rough look at this function, it's going to look like roughly, if I factor this thing out just for fun, you get x squared times x minus 6. So you're going to have something that kind of goes like this, goes down, and then goes up again here, roughly. And so here we are concave down all the way until about 2, and then concave up everywhere thereafter. As for the previous function, this one, 1 over x minus 1, makes a ton of sense. We'd have a vertical asymptote actually at x equals 1. But before that, we'd be concave down, whoop, going like that, and then whoop, something like that. And here we see the concavity fits with exactly what our sign chart says. Now, if you were justifying any of these formally on the AB or BC exams or in a tougher teacher's course, you would need to state the function is concave up when f double prime is greater than 0, and then go through the math. The function is concave down when f double prime is less than 0, and then go through the math. I'm done going through the math. I hope you're feeling pretty good on this. I'm feeling great. See you in the next video. We're going to look at points of inflection there.